Hi everyone, I am Nicolas Bousquet and I will present you the paper Reconfiguration of Spanning Trees with Many Overleaves. So this is a joint work with Takehiro Ito, Yusuke Kobayashi, Haruka Mesuta, Paul Ouvrard, Akira Suzuki and Kunihiro Wasa. So before explaining exactly the problem, let us first start by explaining what is reconfiguration. So basically in reconfiguration you are given two solutions of an instant of a problem and an elementary transformation between any pair of solutions. And you want to determine if it is possible, given my current position, to reach the target one. Okay, so you all know some reconfiguration problem, which is the Rubik's Cube. So in Rubik's Cube you are given two configurations of the Rubik's Cube. Your elementary transformation consists in flipping a face of your Rubik's Cube, and the question is, can I reach my beautiful target position, which is just there. Okay, and so there are many motivations for reconfiguration problems. So the first one is, of course, puzzles like Rubik's Cube or 15 puzzle. And so many one-player games are actually just reconfiguration problems. Another motivation, which is really coming from completely different fields, is Markov chains. Okay, when you are given a Markov chain, you start with some positions or some solution of your instance, and you make some slight modification of your instance at any step. And you want to determine if it is possible to generate any solution by just doing this random walk, and if yes, how much time you need to be sure that your solution is selected almost at random, which consists in the ergodicity of the Markov chain, is it possible to reach any solution, and the mixing time, which is how much time do I need to wait until I know that my solution is almost random. And this is really heavily related with reconfiguration, because, for instance, ergodicity just consists in determining if it is possible to transform any solution into any other. And so these reconfiguration problems has links with many fields. So for instance, statistical physics, where they use a lot Markov chains and they want to generate solutions using Markov chains, but also motion of robots, discrete geometry, where you want to transform some solutions of representation of some graph, for instance, into another one, but also biology, where you want to determine distances between spaces. And in that case, usually you want not only to find a solution, but also a transformation, but to find the optimal one, the length of this solution, which gives the distance between the spaces. Okay, so to sum up, there are three main questions in reconfiguration people are usually looking at. So the first one is a reachability problem. So given two configurations, is it possible to transform the first one into the second one? So basically, for the Rubik's Cube, is it possible to transform my initial position into the target one? Also for the Rubik's Cube, for instance, this is not always possible, but there is a way to determine it. So the next step is the connectivity problem. So given any pair of configuration, is it possible to transform the first one into the second one? So again, for the Rubik's Cube, the answer is no. And the last one is, given two configuration, what is the length of the shortest sequence, if such a sequence exists? Okay, and so this is the question that is mainly looking at in biology, for instance. And all the three questions have indeed their algorithmic counterparts. So can we efficiently solve this problem in polynomial time, in FPT time, in NP, or more likely when it's hard, it's p-space, because many reconfiguration problems are actually p-space complete. Okay, so in this talk we focus on spanning tree reconfiguration. So you probably all know what is a spanning tree. So a spanning tree is a subset of edges that induced a connected graph without cycle that spans all the vertices of your graph. Okay, so for instance, in the left graph, the red vertices for the red edges form a spanning tree. And our elementary transformation between two spanning trees will be an edge flip. So what is an edge flip? It's just you remove an edge of the spanning tree and you replace it with another one. Okay, so here I change the one red edge into another one, and we still have a spanning tree. Okay, and so you can ask the question, given a graph and two spanning trees, is it possible to transform the first one into the second one via a sequence of edge flips? And the answer is yes. And the answer is yes, and the reason is pretty simple. It's just because spanning trees forms matroid, and you know that in matroid you have the exchange property, which is when you have two solutions, when you remove an edge of the solution, you can add an edge of the other solution. So basically it says the answer is yes, and there is always a transformation of the shortest possible length between them, which is the size of the symmetric difference. Okay, so this question is the answer to this question is very simple, but we can ask, okay, what happens if we add some constraint on the spanning trees? Because in real life, usually, in many cases actually, you have some constraint on the size of the spanning trees. So, for instance, the number of leaves. And so in this paper, we focus on what happens if we add some constraint on the number of leaves. What happens if we want that all the spanning trees of the transformation have many leaves, or all the trees of the transformation have few leaves. And so we looked at both problems, and we classified the complexity of both problems, and then we, when it's hard, we also find some polytime algorithm for some graph classes. So first, we can look at what happens when we want few leaves. And so when we have a graph G and two spanning trees have at most k leaves, we can show that the problem is p-space complete, and it's actually p-space complete when we want at most 3 leaves all along the transformation. Okay, and so what you can notice, if we reduce the 3 into 2, so we want a spanning tree with at most 2 leaves all along the transformation, then it's just Hamiltonian path reconfiguration. Okay, so you have an Hamiltonian path, and you want to make some edge flip in such a way all along your transformation, you only have Hamiltonian paths. And the complexity of this problem is surprisingly unknown, because Hamiltonian path is really a hard problem from an optimization point of view, but this is much harder to find some gadgets in order to show that it's hard for reconfiguration. And in the statement, so I say that spanning tree reconfiguration is hard with at most 3 leaves, but we can replace the 3 by any integer larger than 3 in this statement. Okay, so the hard part is really what happened for 3. And we also looked at what happens if we want some spanning trees with many leaves. Okay, so when we want at least k leaves, and in that case the problem is also p-space complete, and it's also p-space complete even restricted to bipartite graph or split graphs or planar graphs. Okay, so we can, with 2 different reductions, we can prove that in these 3 graph classes the problem is p-space complete. But we also provide some polytime algorithms, for instance on cographs and interval graphs for this problem. Okay, and so now in the next few minutes I will try to briefly sketch you and explain you the main ingredients of the proof of these 2 results by giving the reduction and the idea of the polytime algorithms. So first, we want to show that the spanning tree reconfiguration problems, where you have trees with at most 3 leaves all along the transformation, is p-space complete. And this is an adaptation of a reduction from vertex cover to Hamiltonian path. So I don't know if you know this reduction, but this is a very, very beautiful reduction. So let me explain you how this reduction is working, and explain you very briefly how we can adapt this reduction. So this reduction is based on this gadget. So we will create this edge gadget for every edge of the graph, initial graph. So this reduction has 12, this gadget has 12 vertices, and so the black vertices, so basically only the white vertices will be connected to the rest of the graph. The black vertices are not connected to the rest of the graph. And so when you look at this gadget, what is really interesting is that when you want an Hamiltonian path, so you can complete it, you can complete your graph the way you want and connect it to the white vertices the way you want. There is, you know that when you look at the restriction of any Hamiltonian path to this edge gadget, you can intersect this edge gadget in at most two ways up to symmetry for the second figure, which is either you have two parallel paths or you have this zigzag situation. Okay, so you can really complete this gadget the way you want. And what will be interesting for us in this reduction is that you can show that for any spanning tree with at most 3 leaves, so the picture is a bit more complicated, but at least one of the white vertices has degree 1 in the subgraph induced by the edge gadget. Okay, so what you can remark, for instance, is that for this first lemma, when you have an Hamiltonian path, either you have 4 vertices that have degree 1 restricted to the edge gadget, or 2, which are these 2 in this second figure. So when you have a spanning tree with at most 3 leaves, you have less control on what happened on this edge gadget, but you know that at least one white vertex has degree 1. Okay, and so now what is the construction of the reduction from vertex cover to Hamiltonian path? So basically, imagine that your graph is a triangle UVW. So you create an edge gadget for every edge, so for the edge UV, for the edge UW, and for the edge VW. And you also create 2 vertices of degree 1, x1 and x2 here, and k plus 1 vertices that form an independent set where k is the size of the vertex cover. So you want to determine if there is a vertex cover of size k, and so you create an independent set of size k plus 1. And now for every edge, so you take iteratively the edges, and so here this is the first edge, and you connect so there are 2 white vertices associated to U in the edge gadget and 2 white vertices associated to V. So you take the left one, which is the let's say entering vertex for U and for V, and you connect them for X, because this is the first edge we meet for U and for V. Okay, so you make just a complete graph between X and the entering vertex of U and X and the entering vertex of V. Okay, now you take the next gadget, which is UW, and what you do is you have already seen an edge for U, so instead of connecting it to X as you did before, you connect it to the exit vertex of previous exit vertex of U. Okay, so here U, the entering vertex of U, is connected to the previous exit vertex of U, which was this one. And W, that's the first time we met the vertex, W, so we connect it to X. And finally, we have the edge VW, and so the previous edge for V was the edge UV, so we connect the entering vertex of V to the exit vertex of U, and previous exit vertex of U, and we connect the entering vertex of W with the previous exit vertex of W. And when it's done, we finally connect the last exit vertices of all the vertices with X again. Okay, so U, so the last exit vertex of U, we connect it completely to X. We do the same for the last exit vertex of V and the last exit vertex of W. Okay, and so now what you can remark is that so here the size of X is 3. So, and you graph as a vertex cover of size 2, which is, for instance, U and W, and what you can remark is that you have an Hamiltonian path, which is this one. So you start from x1, you go to this first vertex of X, you jump to the first entering vertex of U, you make this one of the two situations of the possible gadget, the previous page, so this one here. And so you continue, then on UV you have two parallel edges, and you continue, you jump to the second vertex here of X, you jump there, and you finally go to the last one and X2. So basically what you do is for every edge gadget, either in your vertex cover you have selected both endpoints and you have the two parallel paths, or you have selected only one endpoint and you have this zigzag graph. Okay, and what you can show is that the converse is also true. Every Hamiltonian path must have this shape. Okay, you really have no choice, and so basically you just have to look at which vertices you select. So which vertices you take the entering and exit edges incident to the entering and exit vertices. Okay, so this is the idea of the proof, and now how do we adapt it for reconfiguration? So first, what we know, so there are many proofs of that result. For instance, Wrofna show that the minimum vertex cover reconfiguration is p-space complete, even on some restrictive graph classes. And so we will show that actually if we have a vertex cover reconfiguration, then we can adapt it into a spanning tree reconfiguration in this reduction, and conversely, if we have a transformation between two spanning trees, we can transform it into a reduction between two minimum vertex cover in the original graph. Okay, so we have, the first thing we have to do is first to associate a vertex cover to every spanning tree. And so what permits to do that is that we have seen in the, when I explain you the edge gadget, we have seen that one of the four wide vertices has to have degree 1 in the restriction to the edge gadget. And so we create a set S of t, given a tree T, which is the set of vertices such that for some edge gadget, one of the two wide vertices of V has degree 1 in the restriction to the edge gadget. Okay? So this defines vertex cover because we know that for every edge gadget, one of the two endpoints has to be in S. But this is not finished because for every spanning tree with atmos reliefs. But this is not finished because we have to show that this set S is not too big in order to be sure that that correspond to a minimum vertex cover reconfiguration. So we need to bound the size to adapt the proof, and we can actually show that the size of S of t is at most k plus 1 for every spanning tree with at most 3 leaves. And what we also have to show is that if we perform an edge flip in between two trees, then it corresponds to a single step modification for vertex cover reconfiguration. So I don't want to enter into details here because it's slightly technical, and the proofs are actually very technical, and I am hiding some details on the statement of these lemmas. But basically that's what we have to show. We have to show that the size of S is not too big, and we have to show that when we perform an edge flip, it corresponds to a single step modification for vertex cover. And both points are actually very complicated and technical proofs. Okay, so this is the idea of the proof for this hardness for spanning tree configuration with at most 3 leaves. And so now what happens for if we ask for spanning tree with many leaves? So I will only explain you how we can prove that this is hard for planar graphs. And so this is a reduction for minimum vertex cover reconfiguration on planar graphs. And so what is the idea? So the idea is we start from our planar graph, and we first subdivide every edge once. Okay, so we create some gray vertices which correspond to vertices in the middle of every edge. Then we create a new vertex for each face, and we connect it to all the vertices, initial vertices of its face, or all the black vertices of the face. And we finally add some pending vertex on each blue vertex. And so now what you can remark is that when you are looking at the spanning tree of this graph, all the blue vertices have to be internal nodes. Why? Because you know that there is a pending vertex attached to it, so you need to take this edge between the blue and the red vertex. And you also need to connect these two vertices with the rest of the graph, and it cannot be connected with the red vertex, so it has to be connected with the blue one. We know that red vertices are indeed leaves because they have degree 1. And we know that when we look at the gray vertex, this gray vertex has degree 2, so at least one of its two neighbors has to be an internal node. Okay? So what does it mean? It means that the number of internal nodes is at least the number of blue vertices plus a minimum vertex cover, because you know that for every edge, one of the two vertices incident to it has to be internal. Okay, and so now the idea is just to show that when we have vertex cover reconfiguration, we can adapt it into a spanning tree reconfiguration with that precisely, so the complement of that instead of leaves here I should have written internal vertices. Okay, and conversely the same holds. Okay, and so we have to check that carefully, but the proof is not that complicated. And so now let me explain in a few minutes how the two polynomial time algorithms are working. So the first on Cograph and the second one on interval graphs. So for Cograph, basically the proof is based on two lemmas. The first one is that the answer for Cograph is always positive when the number of internal leaves is at most n-3. Okay. So the only case that can be complicated is if the number of leaves has to be at least n-2. Okay, so the second lemma is that actually in this later case we can conclude in polynomial time, not only for Cograph but for any graph. Okay. So the number of, so if you want reconfiguration of spanning trees with at least n-2 leaves, then you can decide if you can decide the problem in polynomial time. And so for this second lemma, basically the sketch of the proof is the following. So all the spanning trees with the same set of internal nodes are in the same connected component of the reconfiguration graph. So you can transform any one into any other, because we just have to take an edge attached to a leaf and attach it to the other internal node if it switches between the two solutions. And you just do that for every leaf, and you cannot increase the number of internal nodes during the transformation. And now the second step is that if you are given two sets of size 2, so which are the set of internal nodes, you can decide in polynomial time if there is an edge flip from a tree with internal nodes x to a tree with internal nodes y. Okay, so basically what you can do is really determine if there exist two spanning trees that are incident via an edge flip with precisely these two sets of internal nodes. Okay, and so now let me just explain really briefly how the proof is working for interval graphs by just basically one picture. Okay, so imagine that these two vertices are the two first internal nodes of a spanning tree, and you want to reach a spanning tree where the first internal node has to be this bottom vertex. Okay, this is possible because this bottom vertex here is incident to this one, and this one. Okay, so you can really replace this vertex by this vertex as an internal node, and this is still a spanning tree. But you can do that immediately because these two arranged vertices are only incident to this red vertex. So the only internal vertex to which they are connected are these two arranged vertices. Okay, so in order to transform, to move this internal node into that one, okay, you need to be sure that this one can be transformed into a vertex of degree at most 2 in your spanning tree. Okay, and so far this is not possible if this is the second internal node. So the first thing you have to do is to determine if it is possible to reach a spanning tree whose second internal node is, for instance, this one. Because if the second internal node is this one, then this top black vertex here can be attached to this one, and then now this vertex only has degree 2, and you can remove, for instance, an edge and create this one instead. So remove, for instance, the edge between these two and create this one instead, and this one will become internal. Okay, so to sum up, what is the idea? So the idea is that in order to try to push right the first internal node, we have to push left the second one. Okay, and so the idea of the polynomial time algorithm is really this. So we first fix the first internal vertex of the spanning tree, so which is the red one here, and then by induction, but it is actually a bit more complicated because it is not really induction. We can just delete some vertices of the graph here. We have to be a bit more clever, but it is somehow by induction. We try to push the second internal vertex to the left. Okay, so we try to push this blue vertex into, for instance, this one. And then when it's done, when we have reached the leftmost possible second vertex, we simply have to try to push right the first internal node. Okay? And what we can show is that after doing that, we have reached the rightmost possible first internal vertex of a spanning tree in the connected component. And so we just repeat that again and again and try to determine if we reach exactly the same vertices each time for the two spanning trees. Okay, so again I am adding here a lot of technicalities because the proof is actually more complicated, in particular when the number of internal nodes is not the minimum number of internal nodes. There are some technicalities that appear, but the basic idea is really this. So we want to push right the first internal vertex, and to do so we have to push left the second one to free some space to be able to push right the first one. Okay, so this is basically all the brief overview of the proofs of our paper, and I want to finish with 2 or 3 questions which I think might be interesting to look at. So the first one is for this spanning tree configuration with 3 leaves. So we show that the problem is hard when we only add at most 3 leaves, but we don't know exactly what happened on restrictive graph classes. And in particular, this reduction I show you with this edge gadget here do not keep basically any graph parameters. So it does not keep planarity, it does not keep low tree widths or things like this. So it will be interesting to see if this problem can be solved efficiently on unrestricted graph classes. The second thing is that we, on the proof of Cograph for spanning tree reconfiguration with many leaves, we actually show that the behavior is completely different when we have many leaves rather than few leaves, because we show that with n-2 leaves the problem is polynomial, while for at most 2 leaves we show that we have seen that it is Hamiltonian path reconfiguration which is open. And so yeah, we strongly believe that this n-2 can actually be adapted into n-L for any possible L which is a constant. But a question which I think is really interesting is spanning tree configuration with n-l leaves FPT parameterized by L? Okay, because basically the algorithm we use is we just take any pair of vertices which is possible internal nodes, and we for every pair we determine if there is an edge flip between two trees which have precisely this number of this set of internal nodes. And so this is really not FPT at all when L is increasing. Okay, so this is an interesting question. Is it FPT parameterized by L? And the last question, which may be seem a bit artificial, is what happened in autoplanar graphs. So we have seen that the problem is p-space complete for planar graphs, and so we try to solve this problem on autoplanar graphs, and yeah, in many cases reconfiguration problems are surprisingly hard to decide in autoplanar graphs. So for many reconfiguration problems, that's somehow the largest class on which we can op polynomial time algorithm, but not non-trivial polynomial time algorithms. Okay, so thanks for your attention.